Okay. Are there any general questions? I just sent out an email. I was hoping that the Moodle page on part 1 of this course is available to everyone, but that apparently is not the case. Only to those who were registered for part 1. So I'm trying to work with people in charge of the Moodle page system to make it available to everybody in this class, but I haven't heard back. So in the meantime, I just sent out a link by email to the master set of notes that I was using in the last semester. It's not the notes that I actually wrote. Those are sometimes scribbles. But these are the ones that I would use as a basic reference. So please take a look at those in the meantime, but I'm also hoping to get the lectures available to everybody. Any questions on that? Let me just go to what we did yesterday quickly. So after I reviewed what we did on homoclinic chaos in the last semester as motivation, I promised that we would look more closely into what it means when we talk about chaos. How can we describe it in more precise mathematical terms, hopefully in terms that are not specific to the two examples that I've seen, but more generic. So to that end, I still, in the context of two-dimensional systems, I looked at small perturbations of autonomous two-dimensional ODEs. This was the class of problems that we have seen physically to generate chaotic behavior, or what we want to call chaotic behavior, right? So X is a two-dimensional variable, and F and G, which is sort of the unperturbed system, and the perturbation are C1. I generally use that to guarantee that we have existence and uniqueness of solutions. You might remember Lipschitz is enough, at least for local existence. So I assumed that we have a geometry that we have already looked at and analyzed with the Melnikov function, and in fact detected a homoclinic tangle. And the assumption was that, not the assumption, but rather the approach is that we would straighten out coordinates in a way so that the stable manifold of a hyperbolic fixed point that we know to exist for the perturbed Poincare map would be straight, and the unstable manifold would be also straight for a while, and then come back and do these loops and form lobes, right? The key observation here was that when that happens, and that happens due to the lambda lemma, which I cited, it's an old result that this self-accumulation happens whenever you have a transverse intersection between stable and unstable manifolds. So when that happens, then ultimately there will be an instance, a piece of the unstable manifold will be laid back over this square, and not just the piece itself, but since we are advecting essentially this box along the unstable manifold, gets carried, right, by the unstable manifold into this thin strip. There will be a whole thin strip, part of the image of S, that will have this position. And that prompted Steve Smale to come up with a simplified geometric template or model that he hoped would capture and give some insight into the complicated dynamics that apparently exists here. So this picture then motivated what we call the Smale horseshoe map, which is a very sketchy definition of what we have seen. Basically, a unit square gets stretched first and then folded over. And that action is kind of illustrated by the fate of these two horizontal strips. They get stretched in this direction, right? And they get squeezed in the other direction. And when you're done with that, you fold it over to the original image, because that's pretty much what happens here, right? Now, this picture is symmetric so that we can picture the details well and immediately see what goes where. But you can also imagine that one can straighten out coordinates here, or only take a subset of this and achieve this. So topologically, the two are equivalent. So it's amazing how far one can get with this sketchy definition of this map, as we will see. So far, we've just been asking Smale's original question: is there a set of initial conditions that somehow stick it out and stay in this regime for long times? Because that sort of reflects or would agree with the observed recurrence that we see in experiments. They keep coming back against all odds to an unstable set. And we worked through that, and we found that the set of initial conditions that stay in S, which should be capital S, in one backward iteration is the set of those two vertical stripes, the V1 and V2, right? That's no surprise, that comes from the definition. But as we have worked through this and kept asking the question, are initial conditions that actually have been there for longer, we found that there will be thinner and thinner vertical strips that form a nested sequence of strips that satisfy that condition. What this shows is the set of initial conditions that were in S and have been in S under 2 iterations, backward iterations of the mapping F. Okay, you can actually take this limit, it turns out, by Cantor's theorem, that limit is as a limit of closed non-empty nested sets. Again, each of one of these is closed and non-empty and has these vertical components. The number of those components grows as 2 to the n, and there's the nested nature. And I just appealed to this famous theorem by Cantor that says that once you have such a closed non-empty nested sequence, then you can take the limit, and the end intersection, the limiting intersection is non-empty and closed. And in fact, it's a Cantor set. In this case, it's a Cantor set of lines, which means it's also totally disconnected, as I mentioned here. So the largest connected component is a line. And it's also perfect, which means each such line is a line of accumulation for other lines. Okay, and that's where I stopped yesterday. Any questions on this? Let's go on then. So what do we do with this construct? Well, this is an observation so far that basically tells us, let me draw a sketch as to what we know so far. So when I draw this square again, hopefully it comes out approximate like the square, yeah. And this has been about the 2 vertical segments here, what's happening in there. That in these we have constructed Cantor sets of lines. So they do not intersect each other, unlike in my figure, but they do form a really intricate Cantor set in each case, right? So this type of intersection that we have constructed is basically the union of these 2 sets, the infinity. Perhaps it doesn't come as a surprise that I can now repeat the same question and get very similar answers when I inquire about the forward behavior of points. Namely, if I now ask, what is the set of points, and not only are they in S, but they will be in S in 1 forward iteration, and then 2 forward iterations, and so on. It's the exact same principle, except that the discussion will change here right at the beginning, and I will be talking about backward iterations. Even though I'm asking a forward question. And by analogy, one can work that out, that I'll just say similarly. There will be a set which I denote by H infinity, okay, which will be just the intersection of I going from 1 to infinity of these block HIs. And what I mean by these will be very similar to what I meant in the case of the VI. So basically the set of points staying in the square S under I forward iterations. So these turn out to be, each and every one of them turns out to be it's a set of horizontal strips. And each is closed and connected. And it's a nested sequence. Has the particular one that we're looking at has 2 to the I connected components. Very similar. So one can again take that limit, and by Cantor's theorem, the intersection of these will be non-empty and actually closed. So let me frame that because it's important. Like that. Okay. And what it is then, it's going to be a Cantor set of horizontal lines. I want to show them in this picture, then I need again the original two horizontal strips. Remember those were the H1 and the H2. So this component was the V1, this is V2, and these components were, I think the lower one was H1 and the higher one was H2.
Can I interrupt quickly?
Please.
I think it should be not equal to phi in the frame box.
Thank you. So it's at the empty set, and it's not equal to the empty set. Thank you. Just like here, right? Sometimes when I say something, I mean just the opposite. A good catch. So it shouldn't be the empty set. What ends up happening here is that we have this Cantor set of lines, and I have to have the right color for them. Which again is the set of points, which I characterize as H infinity. Set of points staying in this set S for under 4 or forward iterations. So then, just from the geometry of this, although I'm being sloppy here because, to be honest, I don't have the patience ever to draw infinitely many lines. So invariably, not only is the finite set very finite, but also I don't do a good job making them straight. But imagine that each and every one of those components intersects each and every other component, right? So each line, each vertical line will have an intersection with each of the horizontal lines. So if you add that up, then you can ask, what is the intersection set of these lines with each other? So there will be clouds of points here and there, a lot of them in these corners. And that cloud of points, I think what was my notation, I'll just call lambda, which will be the intersection of H infinity with V infinity. And there's plenty of intersection points. In fact, each connected component of each set intersects the other. And that is certainly a non-empty set. And what it is what we've been asking. The answer to what we've been asking, are there any points that stay in this set for long times? And the answer is that yes. Not only long times, very long times, in fact, infinitely long times in both time directions. So these are points that are staying in S under all forward and backward iterations. By definition, this is an invariant set, right? Because if a point in this set will stay in the set for all iterations, both forward and backward time, then do one iteration, well, that is also in S, right? And also the whole forward trajectory and the backward trajectory, we know will be in S because I just iterated one point that has that property. So this is an invariant set. This is an invariant set under F. F was the horseshoe map, okay? And it's also a Cantor set of points. So really complicated cloud of points. So it is certainly a good candidate to look at, and this is what Smale did, because basically you suspect that this set, which has the remarkable property of surviving on all the instability and stretching and folding. Everything is basically trying to throw you out of there. And yet these points to stick it out and come back to that unstable set. And also they have a fairly delicate structure, right? Because remember, they have all the properties of a Cantor set, which is perfect with all the things I listed here. So perfect, totally disconnected, closed, non-empty. Question?
I have one question. Yes. Well, based on how we constructed the sets V1 and V2 yesterday on this squeezing and then folding operation, I cannot imagine how these horizontal lines would arrive out of the same operations. So on a graphical level, it was clear that these vertical strips would fall back onto these vertical blocks, but I just have a hard time imagining how it would happen for these horizontal blocks.
Well, I don't want to go into that, but I mean, some of you basically have to undo the effect of the horseshoe map, and that's a bit harder to draw. So at this point, I rely on your belief that I didn't want to cover, but it's okay. It's very similar. In the references that it takes just different skills, but perhaps because of the symmetry of the behavior, I mean, the way these slabs behave in forward and backward time. One is mapped into the other in forward time. The other is mapped into the one in backward time. It's by analogy. I was hoping that I don't have to do that.
But do you mean that, for example, that the stretching that we did along, or the squeezing that we did along the horizontal axis and the stretching we did along the vertical axis, it would be actually the opposite in case of the horizontal stripes? Is that what you mean?
So correct. I mean, you have to undo the effect. So first you have to unfold, and then you have to push in this direction and stretch in the other.
Okay. Right? All right.
Okay. So just to spend a second on what this means for the original, because remember, this is a model of some behavior. So the meaning of all this for the original Poincare map, which we are modeling, so we basically started from this construct that we had the hyperbolic fixed point, and we had intersecting stable and unstable manifolds, and all hell broke loose when we had the transverse intersection, which we can detect by the Melnichov function, right? So this was that point P epsilon. And again, what we're modeling here is local behavior near the unstable fixed point. This is where we kind of set up our little trap, remember? So this was S. Now imagine that S is just what you see here. So what we have captured so far is in the corners of S, there are these recurrent points. So if I want to somehow picture that, then one way of picturing is that for a high enough iterate of the Poincare map, right? So this was the nth iterate of the Poincare map. We have these points there. So this is what we're constructing. Okay, so these keep coming back to that invariant set. So that's an invariant set. Invariant Cantor set. For this high enough iterate of the Poincare map. Okay, so that's good to know. But then again, what we have constructed so far is a complicated invariant set. For all I know, once I'm on this invariant set, I may be doing pretty boring things. I mean, maybe it's just, I keep coming back. For all I know at this point, all those points may actually be periodic points. So that means that I do a few loops and then come back. And certainly that by itself would not explain the type of chaotic behavior that I see. So we need to get a little bit into that invariant set. At least we identify the potential culprit for all this, but we need to see what's actually happening within that invariant set. It's very helpful to know that the set is invariant, so I can just restrict my attention to that invariant set. And that's what we are going to be doing now, following the ideas of Smales. So the next question is dynamics within this invariant Cantor set lambda. Okay. So one piece of notation that I will use, I take the original, the Smale horseshoe map. And again, my apologies for the notational conflict. Not that it occurs all the time, but I had another F here. So I now changed that to F naught, all right, not to avoid that, but I just want to be consistent with all the references that I've given you, which tend to call this just F. So that's the mapping. That's the model for the high iterate of the Poincare map. So this is the Smale horseshoe map. And what I'm going to do, I'm going to utilize the existence of this lambda. So I'm going to introduce f tilde, which is really nothing else, just a restriction of f to lambda, right? You can restrict a mapping or a dynamics to an invariant set. You cannot restrict a mapping or dynamics to a non-invariant set because you get out of it, so it makes no sense. But once you know that you start in a set, you stay in this set, you can just sort of, okay, I sort of just restrict my mapping dynamical system to that set. So I will be only exploring this map relative to its behavior on lambda. Okay, and that's fair game because it's an invariant set. Okay, and let me actually copy this here so that we have it in front of our eyes. So I want to have it somewhere here, just as motivation. Okay, so I can refer to it. So what does it mean understand sort of the dynamics within the set lambda? Well, to understand at this point, to be honest, I need to be a bit more specific because I've done a lot of hand waving and topological construction, but if I really want to get my hands dirty and work with an iterated mapping or a dynamical system, I need to have some sort of representation, equations or mappings or coordinates, which I don't have at this point, right? So one natural sort of inclination would be to try to introduce coordinates on this really impossible set, right? Because otherwise, how do I track trajectories? So Smale's tremendous insight was to actually come up with a notion, a good notion of coordinates, and it goes by the name of the itinerary. So the itinerary of a point, which I say might pick here. So this would be, say, a point in lambda. And the itinerary will simply be the forward and backward travel history of lambda under this map f tilde, because you apply the f map or f tilde, because it's written now to P, and for all you know, it's an invariant set, so you might be jumping to this point, f tilde of P. And again, f tilde of P is just f of P, but I'm focusing on the restriction of the map to it. And then again, you apply it again, and who knows, maybe you jump here, right? We don't know at this point, so this would be, say, the second iterate left there, and so on. So this would be the second iterate, all right? So the itinerary would be an encoding which would be the encoding of its history. We'll just say evolution of P in lambda under f tilde. So what do I mean by that? So I take this point, at this point, an arbitrary point from sigma, and I try to, mark its positions as it travels. And the way I'm going to mark that is that I'm going to select the point of reference here. To the right of that point of reference, I will be encoding its forward history. And to the left of that reference point, I will be encoding its backward history. Okay, and I will do that using two symbols, because that encoding will be with respect to always V1 and V2 and H1 and H2. In the forward time direction, it will be with respect to H1 and H2. In the backward time direction, because that's how I constructed those lines, with respect to V1 and V2. So I will just check where it is relative to these sets, and I will only need to keep track of these two indices, 1 or 2. Okay, so I will be using binary digits SI, and they are the elements of the set of 1, 2. And I will be writing, say here, S0, if I find that the application of F tilde to P, the first iterate, sorry, I start actually with the current position. I'm not even iterating it yet, that P is in some horizontal slice, which is labeled by S0. So that can be H1 or H2. So S, the first digit here, will be either a 1 or 2, depending on where I start. In the case that I've shown you here, so this was my choice of P, that first digit, S0, would be a 2 because I happen to start in H2, right? But if I had a point somewhere here or there, that first digit would be a 1 because I would happen to start in H1. I don't stop there, but this is why it's called an itinerary. I will iterate that point once. So I will apply the map. And in this case, I landed here. And I will again check which component of the horizontal line system. And I don't need to check by line. I just check it with respect to these big initial vertical stripes. Which one of those I'm in right now? In this case, I'm in H1. Okay, so my second digit here, S1, will encode that situation because f of b, my first iterate, is in HS1. And I will write S2, okay, which will be the next iterate of that. In this case, S2 will be 2 because my next iterate is there. So I'll just write f second iterate of p, and I should have a tilde. Not that f and f tilde are the same, except that they're in terms of their action, but they're restricted. The f tilde is restricted to the restriction of f. So this is p, and it's in H as 2, and so on. And I keep going. Is this a well-defined procedure? Can I go forever? Yes, because this is an invariant set, and I know exactly where the invariant set is located. It never gets outside H1, H2, and V1 and V2. At every step, I will have an answer, because at every step, I'm somewhere in this cloud. The cloud has 4 components. I will be able to answer this question uniquely, which one of those, H1 or H2, contains me at that point. So I can keep doing this forever. I can also ask now about the backward history, and I will similarly encode the backward history in the same way. So I will check where I am now with respect to the V components. And my digit at this point, S-1, will characterize my position with respect to the V vertical strips. So in this particular case, this was my P. My H2, my position with respect to the horizontal stripes was clear. I was in this one. I was in this stripe, right? So that gave me the 2 in this case for S0. But I also checked my initial position with respect to the vertical stripes. And my initial encoding in that regard is a 1 because I'm in V1. So in this particular case, this symbol that I'm referring to here, and it can take values from 1 or 2, would be a 1 for this particular point. But I have lots of other points, right? So it's a procedure that's well defined for all of them. I don't stop there. I then ask, what is the pre-image? Again, this is not the inverse because this map is not generally not, I have not argued that it's invertible on the whole domain, certainly. Well, I know that it's continuous, but it makes sense to talk about the pre-image of P because it's there since it was coming from somewhere, right? So at this point, I don't know if the map is invertible. I can talk about the pre-images, but then I can check the pre-image, and at that point, well, I'm using the fact that if you actually do some work, you will see that within this lambda set, the map is invertible because I can't have 2 different encodings at this point. I cannot talk about 2 possible pre-images residing in different sets. So let's just take that knowledge for granted that within lambda, in fact, this can be shown to be an invertible map. So I'm asking where is that pre-image, and I will say the answer to that is S-2. So this is my next digit here, and I can keep doing that and encoding things in backward time. So the second pre-image of P would be in V S-3. Okay. Again, this is a well-defined procedure because within lambda, I keep going and I will not leave lambda because it's an invariant set, all right? So I now have a doubly infinite sequence, which I call the itinerary of P. And let me write that out, that this is a double infinite sequence. And one thing that I'm not showing here, but you can find in the references, it takes a bit longer to show that this mapping, which is now a real phi, not the empty set, which is a map from my invariant set into the set of symbols. So this is the symbol space, the space of doubly infinitely long binary sequences. So the map that actually associates the itinerary of a point to the point is a homeomorphism. So it means that in the appropriate metric, it is C0, so it's a continuous association, meaning that if I take two close enough points in this set here, then the associated symbolic encoding will also be close enough. At this point, you might ask, I know how to take two close enough points in this invariant set lambda because this invariant set lambda sits on the plane and I have a notion of distance on the plane. But how can I say, and I need to say that to define continuity, how can I say that if I'm close enough in lambda, then the two symbolic encodings will be also close enough? I need a notion of distance. I'll get to that soon. I will define a metric, a notion of distance on sigma. At this point, I'm just relying on your intuition that if 2 points are close, then and I'm mapping them under a continuous mapping, then for a while, they will be traveling closely to each other, right? That's just because I'm applying a continuous map to them, right? Therefore, if they were close, then if I take another point now here, which was close to P, and then the image of P is here, then somewhere there, I will have the image of the other point. So for a finite number of iterations, they will be traveling together, both close, both in forward time and backward time. Therefore, their encoding will keep being the same for a while. And that turns out to be, in fact, the right notion of distance in this symbol space that I'm going to get into, is that we say that two of these binary infinitely long, doubly infinitely long sequences are close to each other. I'll get to that. If they agree on large central blocks, if they agree on initial iterations, forward and backward time, at least for a while. And we're not going to care so much about what happens afterwards. So the metric will not care so much about their distance here. It will emphasize their distance here. That's the metric that I'm going to get to. So with respect to that metric, it is true, it's a believable statement that if you take two close enough points, then their encodings will be close, okay? So this is C0, but being a homeomorphism is more than that. It also means that the map is invertible, okay? And also the inverse has the continuity property. So C0 and has a C0 inverse. That's, I'll just say C references. Okay. What that means, though, that this is a very good encoding. It means that it takes close points in lambda and associates coordinates to them that are close to each other. In fact, if I make 2 points approach each other on lambda, then their coordinates, these bi-infinitely long sequences, will also approach each other. And not only can I do it in this direction, but and this is really important, that this is a homeomorphism and hence it's invertible and continuous, that I want to actually be working with the itineraries. I don't know much about what happens in lambda. I want to understand the dynamics of the itineraries because those are good. And I finally have a coordinate system. I want to work in these coordinates. And whatever conclusion I reach, I should be able to translate it backwards. And if I didn't have an inverse, which is also continuous, then that translation would be non-obvious because who knows what two close enough symbol sequence gets mapped when I map them back to the real sort of physical space. So these are very important. So this is a homeomorphism. So basically the itinerary is a good coordinate system. Coordinate system on sigma. Now, sigma looks like a boring space. Well, I just write ones or twos, or if you want zeros and ones endlessly, I mean, everybody can do that. But to appreciate the complexity of sigma, you can also view sigma as the outcome of an infinite coin tossing experiment. All outcomes of heads or tails, you mark heads with 1, tails with 2, are contained in this space. So there's basically a probability space. It's very rich in terms of outcomes. So that's already kind of a warning sign that, wait a second, I can have some pretty complicated dynamics in this space, because look at the variety of outcomes that I can observe for a coin tossing experiment. So the thing to know that the sigma also coincides with the space of outcomes for a random, infinitely long coin tossing experiment.
Could I ask a question?
Right?
What is the topology of this set lambda?
You're breaking up, you are. I don't know. Perhaps you could repeat now?
Yeah, what is the topology of the set lambda?
The topology. We haven't defined any topology yet, so it's just a set of points. So there's two sets here. The sigma, that's not what you're asking, the symbol space. It's the lambda that you're asking.
Yeah.
Right? So the lambda is four basically components of Cantor sets. If I want to do any topology on them, I'm lucky because they live in R2. They inherit the topology from R2. I can just take any notion of distance that I have in R2, any collection of open sets, and I can use that to define distances and relatively open sets in lambda, because they are just ordinary points in the plane. Okay. The bigger question what do I do with sigma? Because sigma is an abstract space. It doesn't live in R2. Okay. And I already made a statement that assumes that I have a notion of a distance in sigma, and I gave a hand waving notion for the distance. Once I have a notion of distance, that's a metric space, and I can define open and closed sets based on that, on sigma, right? I'm going to get to that. So, but basically first I wanted to say that even if you don't want to get involved in the topology of sigma, like I said, the topology of lambda is given because it lives in R2, inherits the topology of R2. It's already good to know that this relationship between the two is a good labeling relationship. So I'm going to get more to the distance on.
What I'm wondering is, does every point have adjacent points that are also in lambda? Or are they just
adjacent point? So these are Cantor sets, right? So the largest connected component is a point. So that they don't contain any intervals, open sets, or anything. You can talk about relatively open sets by intersecting lambda with an open set of R2, but it's a perfect Cantor set. It's just cloud. It's a Cantor cloud of points. Right?
Can I ask a question?
Yeah.
So for phi to be a homeomorphism, is it necessary for F to be at least injective?
F tilde.
Yeah.
Right. Yeah. So that's a consequence then. F is very sort of generously defined. We can certainly on the subset that we defined F on, it seems to be nicely behaved. The issue here is that we never said what it does on other points, right? So that's the missing link in the definition of F. But what it turns out that the way we have defined F, which was pretty nice, just in terms of its action on horizontal and vertical strips and so on, is enough for us to obtain a nice map, F tilde restricted to lambda. Okay, so on that set lambda, as a consequence of these actions, it turns out to be nice, right? That's a consequence, even though I never exactly defined actually at each and every point of S what exactly the map does.
Okay, thank you.
You're welcome. So it's not injective on S because clearly you're losing points. Just imagine that you did the fold, right? And part of those points are out, so they left. They're not gonna be injected. But the construct is such, is powerful enough that on that set lambda, it's pretty nice. Okay. What did I got distracted now, but keep asking questions. It's just I had a story to tell. So this is only, while my ultimate goal is to understand the dynamics on lambda, I've made one step. I have basically introduced coordinates on sigma, which is its brother, right? But I still don't know what the induced dynamics is on sigma, right? Things are jumping around in lambda, which is this set here that Smale was considering originally for the map. It lives in R2. It has a direct relationship of what I would see in a Poincare map, but I'm working towards transferring that problem to an abstract space. And the abstract space is sigma, is the outcome of coin tossing experiments, right? What I did, I've introduced a set of coordinates, but I need dynamics. I need to be having an equivalent dynamics, which is equivalent to what the map does in lambda, okay? So I need to see what happens when I actually map this point forward, P, or backward into its images. What does that translate to in the symbol space, okay? So in order for me to understand that, I need the encoding of iterates of P, right? So we will probably see the parent. So P was in lambda soon. So the big question is that if I now look at F tilde of P, which is again, remember just F of P restricted to lambda, what is the symbolic encoding of that, right? So if that's an element in lambda, so I can take this mapping and its image will be the encoding that I'm after. And the question is, what is that, right? I know that it has an encoding. What exactly is it? So if I write F tilde of P and I associate a symbol sequence with it, only thing I know for sure it will have a dot, right? But what is the encoding of that given the information that I already have? Now, given the information I already have, I have to find the positions of F tilde P to get the forward encoding with respect to the horizontal slab. So F tilde P, how does that behave relative to the horizontal strips? Well, actually, I have that information. I've already worked with that information. I figured that out. So right here, when I was doing the forward encoding of P, I answered that question. This point, F tilde of P, is in HS1. So the first location here will be S1. And that's because I already know that F tilde P is in HS1. In order for me to get the next digit here, I need to figure out what the first iterate of F tilde P does relative to the horizontal strips. But the first iterate of F tilde P is just the same as the second iterate of P in forward time, right? And I've already figured that out, because if I scroll back here, I answered that question already. That was in HS2, which was this digit, okay? So I can just write S2 here, and so on. It looks like once I know the encoding of P, then at least for this part, it's easy to figure out what the forward encoding of F tilde P, the iterate of P is, because all I need to do is just take these digits that I've already figured out and shift them to the left. Now, this reasoning doesn't quite apply yet to the rest of these, but I figured out how I can handle the forward encoding of P given this information, okay? So that's good to know, but the puzzle is then what happens here. Now, one thing to note, so this is just sort of one piece of information, recall that F, the map, the underlying map was defined in a way that it takes the horizontal strip S0, right, and maps it to VS0. So it takes this horizontal strip, pushes it in the direction, stretches it in the other direction, folds it over, and there you go. This is how we defined the VIs to be the images of HIs after that operation. Okay, so that I know for sure. So if I now take a point, P was originally in HS0, that was my assumption, and I apply F to it, but the F is now restricted to lambda. So when I evaluate F on a point in lambda, that's just F tilde P, that's going to be in VS0, right? That's a very important piece of information because that's exactly the kind of thing I need to answer what goes here. Remember, that was the principle for the encoding, that once I have checked, in order to get this digit, I needed to check where I am relative to the HIs. In order to get that digit, I needed to check where I'm at initially relative to the VIs. And for my current point that I'm encoding, the current point I'm encoding is this. So the answer to that question is then S0. That's good. So then maybe let's do one more. If I then need to find, how do I fill in the next blank here? I need to see the first pre-image of this point, and I need to see where that is relative to the VIs. So I take the first pre-image, F tilde inverse, right, of F tilde P. That's what I'm doing to find its next digit in the encoding. But F tilde inverse F tilde, they cancel out, so that's just P. Okay? And P was encoded to be in S-1, remember? That was here. So therefore, what I need to write here is S-1, and so on. So then when you continue this, you'll probably believe me that this is then S-2, and so on, which is amazing, because basically what it tells you is that one iteration of P, and that's what I'm encoding here, in the real space where lambda lives, is equivalent to a very simple operation in the symbol space, namely just one shift of digits to the left, right? So that's an incredibly simple dynamical operation that I can really perform without too much trouble. So this is then the encoding of F tilde P in sigma. Okay, so the consequence of this is that the dynamics of F tilde is on sigma is equivalent to this operation just shifting to the left is called the Bernoulli shift map to the left on doubly infinite binary sequences. So the Bernoulli shift map, sigma, I would say, let's give it a name, will be an important map. Just simply define sigma is a mapping on this large space, capital sigma. What it simply does, if you have S encoded as S0, S1, S2, and so on, not encoded, that's sort of, this is basically a representation of S, S-1, S-2, blah, 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 then sigma of S is just one shift to the left. So it's going to be S1, S2, blah, 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 S0, S-1, S-2, blah, blah, blah. remarkably simple. So that I find pretty amazing, that we have this fairly vague definition of a mapping. And what we have found that with no coordinate systems, just sort of hand waving, right? You can actually find a space with coordinates in which you have an explicit form for the representation of this map, which is very simple, deceptively simple, shift to the right. The catch is that this is on an incredibly complicated space because it contains all the outcomes of a coin tossing experiment. So very simple dynamics in a very rich space, right? So to write this down more in a way that topologists like, it's the following, that if you take the sigma space, then little sigma is a mapping on them. And I can get to that by taking the original dynamics and lifting it up through this encoding, this phi, which is a nice mapping. It's basically the one that introduced coordinates on what? On lambda. This was my invariant set. And on that original lambda, I had my F tilde. Because phi is a homeomorphism, it is invertible. And also the inverse is nice and continuous. So this diagram commutes. And that relationship means, the commutation relationship, that I can understand F tilde, which is a very vaguely defined and fairly complicated map on lambda, and the restriction, remember F tilde was the restriction of F simply to lambda. I can, what does F tilde do? It goes from here to there. But equivalently, I can go first here, then I apply sigma, and then I come down using the inverse. So that is the same as applying phi first, and then concatenating it with this really simple Bernoulli shift map, and then applying the inverse of phi. And this is a formula that we have seen in part 1 of this class. When two maps were related like this to each other, we were happy because it meant that they have a deep topological relationship. That we had a name for these. These were called topologically conjugate mappings, and they shared orbit structures, including their orientations. So the consequence is that F tilde in the language we have used in part 1 is topologically conjugate to the Bernoulli shift sigma, okay? And a consequence of that is that it's enough to understand the orbit structure of sigma, even intricate details, because whatever orbit I find for sigma, whatever property, it will be inherited in the appropriate sense by the original mapping F tilde. So orbit structure. And in appropriate sense, you know, the topological conjugacy preserves the orbit structure and also the parametrization of the orbits. In continuous systems, we would say by time, but here by iteration number. So I keep iterating sigma, make conclusions about its discrete orbits. Suppose I get a periodic orbit, same conclusion immediately applies to lambda. It would be very hard to find a periodic orbit for F tilde on lambda because I know so little about this. But let's just see how simple that is to find actually orbits like a periodic orbit for sigma, because now I have coordinates. So let's invest a little bit in trying to understand the dynamics of sigma on capital sigma. Because this relationship tells me that I can get a lot of mileage out of that. Practically whatever I understand about little sigma on sigma will carry over to F tilde on lambda. And then in turn, that's a statement about a high enough iterate of the Poincare map, right? It's a pretty powerful tool then. So what is the first thing you ask about some unknown dynamics in any space? as I mentioned repeatedly in non-linear dynamics. One, look always for the simplest things. What are the simplest things? Fixed points, right? So this is the first question. So fixed points of sigma. What is a fixed point of sigma? Well, it's a symbol sequence built out of 1s and 2s that would be kept fixed by sigma no matter how many times you iterate sigma. Well, if you think about that a little bit, that symbol sequence has to be fairly special, and you essentially only have two choices, all 1s or all 2s. Because if you have any variation anywhere, then after the shift, you have changed the structure of the symbolic encoding. You cannot have, it should be completely invariant with respect to the application of sigma. It should be mapped into itself, right? So the two possibilities are 1s to my left and 1s to my right, nothing else, or 2s to my left and 2s to my right. Now I will be working with these endlessly repeating either single digits or fractions, not fractions, sections of digits, right? And the infinite repetition in this business is typically denoted by an overbar. It just means I only write a finite piece, put an overbar. That means in the appropriate direction, just keep repeating that. That can be a single digit or it can be a finite number of digits. When I put an overbar, it means a repeating block, okay? So with that notation, I write 1 overbar, which means 1 repeats itself forever and 1 repeats itself to the other direction forever as well. This is one fixed point. And the other possibility is that I have 2 repeating itself. And again, the overbar, it means an infinitely repeating block. That's pretty much it. Now try doing the same exercise for F tilde in lambda. I didn't even give you details. It's not clear at all if it has a fixed point or not to begin with, right? Here, we can read it off immediately without doing any work. And it doesn't stop there, because now let's go for what's the next more complicated thing for a mapping, fixed points? Well, now periodic orbits. What period? Well, period 2. So that means it's not quite a fixed point because I go away under one iteration, but then I come back, right? So what are the period 2 orbits? You need to think about symbol sequences that don't, under one iteration of sigma, don't map into themselves, but under 2 iterations of sigma do map into themselves. So they have to have some periodicity. So if you actually think about that, you will find, and you don't want to count fixed points, because fixed points obviously come back to themselves periodically, but we look for the minimal periods. So I would say the minimal period is 2. That's what defines a k-periodic orbit, that's the minimal period, right? So the minimal period being 2, actually, if you think about it, it's only satisfied for the orbit, which is built out of these points, 1, 2, 1, 2, and then you apply sigma to it, you shift it to the left, then it becomes 2, 1, 2, 1. And then when you apply sigma next time, you recover the first point, right? So basically the thing to, so this is basically just one orbit, but it has 2 points. So the thing to imagine is that you start from this point, say 1, 2, 1, 2, and again, infinite repetition, all right? You apply sigma to it, that's another point in this abstract, I'm drawing points now in sigma, it's an abstract space. So under the application of sigma, I applied sigma to that. I obtain 2, 1, 2, 1, because there's one shift. And then I apply sigma again, and that takes me back to the original point, right? Because if I do a left shift on this symbol again, I recover the original point. When you try to play with this, you realize this is the only one you can find. there's two notions here, the periodic points, which are elements of a periodic orbit. Of those, we have two, but they form the same orbit. So if I could start here, I could start there. It's still the same orbit. So the number of periodic orbits of period 2, minimal period 2, is actually 1. Again, try to do that directly for F tilde, for the Smale horseshoe map. That's pretty hopeless. And here, it's almost trivial. So luckily, because things are so simple, you can keep going. And well, let's do maybe, since in the notes, I also did period 3. So just we get a sense of how it works, and also get a glimpse a little bit of the sort of the non-predictability or not obvious predictability of the number of period 3 orbits. So if you think about that, you need to be able to come back after 2 iterations of sigma, but not before. So the points that correspond to that, so say 1, 1, 2, 1, 1, 2, right? So if you then shift this by 1, you get 1, 2, 1, 1, 2, 1. So you certainly didn't come back to the same point. Shift it again, you get 2, 1, 1, 2, 1, 1. You're not back to the same point, but then shift it again. So you get 1, 1, 2, 1, 1, 2. Okay, so how many times have you done the shift? How long did it take for you to get back? This was 1, 2, 3. So this is a period 3 orbit. Okay. Are there any others like that? And again, 3 has to be the minimal period. Well, if you think about it, there aren't too many others. There's one which is fundamentally different, 2, 2, 1. And the actual order, when I list something first, this is no more distinguished than that point, right? I just wanted to get my hands on one of the points. So these are all equivalent points in the same orbit. It just so happened that I picked this one. And for the other one, I'm going to pick this one. And if you go through the same shifts, then after 3 shifts, you're back to 2, 1, 1, 2, 1, 1. And if you try your luck with others, you will find that the only way you could do that is actually start including the fixed points, but those are fixed points. So basically, you have 2 orbits, 2 such orbits. There's no pattern so far because there were 2 fixed points, which is basically periods 0 orbits. Okay. That's not right. Period 1 orbits, if you will, because already 1 iteration takes you back. So I take you back. So these are, take that back. So these are period 1 orbits. These are period 2 orbits. Of these, you had 2. And then from the period 2, you had 1. And then at the period 3, you again had 2. So there's no obvious pattern so far. It's not that it's increasing. There will be a homework problem. It's really not hard to do that if you go up to period K, then there's a nice recursive formula for the number of such orbits. So the number of such orbits, and this is the minimal period, K periodic orbits, right? This is the number n of K. You can get that by evaluating 1 over K, multiplying 2 to the K, and subtracting the sum of I times Ni, where Ni just refers to things you have already computed for lower indices than K, because this summation is, well, this is the notation in that community. It's not an inner product, because it will not have a result, but this symbol just means that I divides K. It's an integer divider of K, so any number that can be any integer that's a divisor of K. So that's a general formula. And this will be C homework, which you will get soon. So you do have a formula for this, and it's not a simple formula. It's not linearly growing. It's not quadratically growing, but it will give you a non-zero number because none of these were 0 to begin with. There will be a nice number. It actually will be growing, as you will see. So for each and every K, you have first the construct of the periodic orbit, because you can certainly write them down like I did here specifically. So you have the coordinates of the periodic points and the orbits, and this is the number of orbits. So if you put that together, there's actually a really striking conclusion that this sigma, although it looks like a very simple map, even in terms of the periodic orbits, it's very rich, because it actually, when you continue this argument, it has a countable infinity of periodic orbits of all periods. So it's not true that for each period you have a countable infinity of orbits, but altogether, you name any period, there will be periodic orbits of that period. That is already unusual for a map. And altogether, you can arrange them into a sequence which is countable, right? So sigma has a countable infinity of periodic orbits. So what's countable infinity? Just to recap that, a countable infinity, something is infinity if it's not, the cardinality of something is infinity if it's not countable, it's not finite, that's not true, not countable, not finite, right? So this is one kind of infinity, which is still countable, meaning any set has the cardinality of countably infinity if you're able to arrange its elements into a well-defined sequence so that each and every element of the set will have a tag. So I have infinitely many points, and I just pick one, and you will be able to give me a number. Say, oh yeah, wait a second, that's actually 10,247th in this sequence. So one can order them into a countable sequence. That's countably infinity. For instance, rational numbers, integers, the clear example, right? Infinitely many, and they're conveniently already ordered for you. But another famous example is the rational numbers within, say, 0, 1, which is quite a lot, but they are still in minority relative to all the numbers between the 0, 1 interval, right? So it has that. So in order for me to show that's something I can show here based on what we have, because it's not too complicated, all I need to do is actually demonstrate that I can order it into a sequence. So order periodic orbits into well-defined sequence. How do you go about that? Well, you start writing them down. So it says, okay, period 1, which is the fixed points, I had 2. It doesn't matter what they were. I put them one by one next to each other. Now, it has to be well-defined. So whenever I will be putting down sequences next to each other, I will have a well-defined, or I will need to have a well-defined ordering scheme so that I can reproduce that ordering. What would be a logical, the simplest one? Well, the simplest one you could do is just look at these sequences and treat them as numbers. Forget the dot there. And whichever is the smaller between the two, you write that first. So view them as decimal numbers, take the dot away. This is usually called lexicographic ordering, and that will give you a well-defined ordering. So here I will say, generally speaking, use a lexicographic ordering, which means treat symbols as decimal numbers. I mean, ordering real numbers given in decimal digits, right? You will not see all sorts of digits, 9 and 8 and things like that, but you will see 1s and 2s, right? So that gives a well-defined ordering in this sequence. Then I ask k equals 2. And again, I will have a systematic procedure of, I can write down my periodic orbits. I have to count the orbits, by the way, not just the elements, but for the purposes of counting the orbits, how do we do this? For the purposes of counting the orbits, I will need to count these collections, not the individual elements. Okay, so within those, you just write down, say, a lexicographic ordering, starting with the smallest one, and then gives you a number, an extended number, a long string, and then compare that to another periodic orbit for which you have done the same. Okay, so concatenate. into orbits. This is sort of a minute detail. You can do it in many different ways. The point I want to get to is that when I say take stock at each k, I have to have a scheme by which I order these. And then you can have many different strategies because all you have is always at some point a finite number of binary digits out of which you build what you call orbits, right? And then you say that one orbit comes later than this orbit in my sequence. And you figure out your own scheme, whatever it is. The simplest one is copy all those points and periodic points in the same orbit together. You get a number, do the same for the other orbit, and compare these two as numbers, as if they were decimal numbers, and whichever is smaller than the other, write that first. So you will have then, for k equals 2, all that exercise is moot because we only had one such orbit, remember. So here we actually had one. And what I'm doing here, I imagine that I systematically go like this and order these periodic orbits into a sequence. K equals 3, how many did we have? We had 2. So I just write this down. 1, 2. I keep building this sequence. I keep copying them next to each other. So when I go to, say, k equals little n, then I've already done all the homework up to that point and now start listing the corresponding periodic orbits. I have nk of these. The formula is above here, right? Whatever that number comes out to be. And I have an ordering scheme for them, and I can keep going. So, right? So the end result is a well-defined ordered sequence of periodic orbits. So it's countable. I have a scheme for ordering it. What makes that possible? What makes that possible is that I have incredibly detailed knowledge of these orbits. I can explicitly compute them, but very rare for a nonlinear dynamical system for any k. I did that for the low ones, but I give you any finite k, you will be able to play with combinations of numbers and get these. And also I have a complete understanding of their numbers, right? It's also that I can keep going, and I know that that will not hit 0 at any point, hopefully. That would be an interesting exercise to show. Even if it hits 0 at any point, it doesn't stay 0. Suppose it's 0 here, right? It will not 0 out. So one member here is 0. It will not make all the others 0. So it keeps adding up. So that's pretty remarkable if you think about it. We still know we have no coordinates for the original mapping, but in this sigma, we have already arrived at a very powerful conclusion. You will see periodic orbits of arbitrary period, which means that you will observe motions for that beam or for the transport of particles between different cells in the convection problem that for arbitrary long times will not appear periodic because they will only become periodic after an even longer time. So this is the significance of having periodic orbits of arbitrary period is that, I turn that around. They only show signs of periodicity at that point once you have reached that high number. But so this starts showing of longer and longer chunks of perceived non-periodic behavior. So it's not that things will be repeating themselves. So this is pointing in the right direction. With that, however, comes some bad news as well. If you take some closer look at these periodic orbits, it turns out all of them are unstable. So that means that you will never observe them. You may travel along them for a while, but then you will depart from them. This would be very hard to show for a conventional dynamical system defined on the plane, but it's amazingly simple to show for a dynamical system defined by the Bernoulli shift map. So I want to get to that now. So I think that the next point is that, however, all these orbits are unstable. Now we're talking about not just fixed points, but periodic orbits, and you've seen all the hassle. We talked about a little bit about Floquet theory for linear systems, but to show that a periodic orbit is unstable analytically, conclusively, that's very hard. It's unrealistic in our usual setting. In the symbol space, in the symbolic encoding, everything becomes possible. So how would you do that? Now for the instability, I can't avoid anymore having to define a metric, because the notion of stability is always, it always involves distances, right? You say what something is stable. If I start close enough, I stay close enough. Something is unstable if in backward time I get closer and closer. So I cannot avoid any further to be more specific about the notion of distance. So to talk about stability, we need a metric on sigma. And that metric is the one that I outlined already, which intuitively deems 2 points, 2 encodings close if they agree on large central blocks. And if they start differing further away, those are results of long iterations of the original map. We don't worry about those so much because we know that initially two close points would separate anyway, even if they are super close, right? So what is that metric? That metric D will be defined on sigma cross sigma, and it maps, as any metric would have to map, into R plus union 0. So it can give you 0 distance, or it can give you positive distance. And the way you evaluate that metric is that if you take a symbol S and S bar from sigma, so 2 elements of the symbol space, then the metric defined between them, the distance between them, is what I have just said. Basically, you form an infinite sum. These are double infinite sequences, so the sum has to range from minus infinity to plus infinity. And what you will be doing, you will be digit by digit comparing the 2 symbol sequences. You will be comparing their appropriate digits. So you take the ith digit of S, and you will be subtracting the ith digit of S bar. This difference can be either 0 or 1, nothing else, right? Now, if I kept adding this up, then pretty soon I could reach, not soon, but I could certainly reach any high number, and I could go to infinity. And that's not good for a metric, because if this sequence is divergent, then the metric is not well defined, right? So the way to make this well-defined actually coincides with the idea of discounting more and more the difference in larger or further away placed digits. So I simply do the following. I normalize this by 2 to the I norm. So that means that I attach less and less weight to differences that occur at larger and larger digits. However, this will certainly deem things close if I only pay attention to the central block. So this metric, so symbol sequences agreeing on large central blocks are close. So you can show that actually sigma in this metric, actually, you can see that this will give a finite metric for anything for any distance in the space. For any 2 points are separated by a finite distance, in fact, very finite, because the DSS bar, if you try to sort of see what the worst case distance can be, I take out the 0th element of this sum, right? So well, first I do a quick estimate before I do that. So this is less than or equal to what? I mean, the worst case scenario for this distance is when this hits 1 for each and every digit, right? That's the largest separation I can have between the digits. So this is less than or equal to, from minus infinity to infinity, 1 over 2 to the I norm. That I need that because I also takes negative values, but I care about the norm of I, because that tells me how far I am from that reference point in the middle. Now I take the I equals 0 element of this. 2 to the 0 is just 1, so that's just a 1. And I can just write this as a one-sided sum twice from 1 to infinity, right? Of 1 over now 2 to the I, because I is now, I only take the positive I range, but I double it. That's why I have 2 there. That sum is well known. That's just a geometric series, so that's equal to 1. So altogether, this is 3. So I have a universal upper estimate that no 2 points can be more than 3 apart. Okay, so that means that this is a bounded space in this metric, and also you can work this out in this metric, that any Cauchy sequence, which means that adjacent elements of the sequence get closer and closer to each other, will converge to a point which is still within this space. So it's also a compact space. So what sigma then becomes is a compact metric space. Good thing is, this is perhaps too much abstract mumbo jumbo here, which we don't need all that much. For those of you who are interested, I give a little bit more than necessary. The point is that we do have a nice metric way of measuring distances on sigma. And sigma is, even though it's an incredibly diverse space, with respect to this distance, nothing is going to infinity. It's a compact space still. And the distances are actually not too large. So things will not have an opportunity to avoid each other all that much. They cannot separate to each other with huge distances. In fact, it's bounded. So this is sort of a hallmark of what we're heading towards chaotic dynamics, is that to develop large, complicated behavior relative to each other, well, complicated behavior, for instance, strong separation, is only a big deal when you don't have all the space to go to. So it's really a big deal when you're in very limited space, and yet you're trying to constantly avoid the other players. If you have an infinitely large space and infinitely many players can easily avoid each other just by increasing their distances. So in fact, we're heading towards a description of chaos that also this compactness will be essential. So now I have a definition of closeness, and I can really check my statement about stability, and that's probably the last thing I do now because I finished earlier. So now with this notion of distance, we can now talk about stability and instability. So that can be discussed. And the claim was that all these periodic orbits are unstable. So take a period K orbit. And any a point in that orbit, a K periodic point, is something like this. So I take a finite symbol sequence, I call it A, it has length K, and I repeat it on both sides. This is what these orbits look like, right? And that K can be large, K can be small. I can do this for any K, right? All of them look like this. So what I do then, I consider another point, like other symbol sequence, which I engineer in the following way. Consider an arbitrary finite string of symbols and call it B. Okay, so that is just basically a symbol set B1, B2, blah blah blah, B, say, what do I call it, capital N, and was arbitrary. And I just built this out sequence, and it's just a sequence sitting by itself of strings, and the BIs are taken from this set 1 or 2. And what I will do, I now consider a modified version of A, which I get in the following fashion. I leave, for instance, the right-hand side of A unchanged, and I take my B, I squeeze it in here, all right? And then I write A, and I repeat it endlessly forever. And so if I have called this, say, let's call this point S, and let's call this S star, okay? Construct is clear, right? I'm tinkering with a periodic point. All I do, I'm sort of messing around with the first capital N digits. And then after that, I let it run the same way as it did before my modification. Now, clearly, I select B in a way that I forgot to say that it's by no means equal to A. Okay, so this is a strange foreign entity that I squeeze in there. Even if it has the same number of digits as A, it will differ from that, but in fact, it may have many digits or many fewer digits than A. Okay, so it's different from A, right? So as a result of that, if I start iterating, and here's my problem with the capital N, to be consistent with the notes, let's call this capital K, right? If I then start iterating S, and I start iterating S star, what's the iteration doing? I'm going to check their distance. What's the iteration doing? The iteration is shifting things to the left. Now imagine that you keep shifting this A to the left, but new versions of A keep coming, right? So by shifting things to the left, this B, which now actually mattered a lot in terms of distance initially, because it was very close to it's a central block, it gets shifted to irrelevance, because it gets shifted to domains where the difference between S star and iterated image of S and S star start not mattering, because you start paying a huge penalty because B is now shifted away from the central block. So even though initially I have a distance between these two, which is sizable because B is very different from A, after a while, it's not going to matter. In fact, the difference is shifted to infinity. And as a result of that, this distance will go to 0 as the number of iterations goes to plus or minus infinity. Okay, so what does that mean pictorially? Here I had the periodic orbit, the K periodic orbit pictorially, right? So it had all the K periodic points. I was jumping between them. And what I have effectively constructed is a homoclinic orbit to that, because I started with some point here, and this is certainly off that periodic orbit. This was my starting point. This was S star, right? And this was just one of these points S there. And what I'm finding that in forward and backward time, this orbit just keeps converging to the same periodic orbit, right? You jump along that, because that's exactly what I'm finding here. So it keeps running closer and closer. So what this generates, therefore, this is a homoclinic orbit to the K periodic orbit. And as a result of that, the K periodic orbit is unstable. Why? Because that's what a homoclinic orbit means. It means that in backward time, at some point you were incredibly close, and it doesn't matter how close you were, you're reaching a very finite distance. Okay, so that homoclinic, yes, you're going back, but it also means that there's a mechanism that takes you out of an arbitrarily small neighborhood of that periodic orbit. So this is unstable. And in fact, the one final thought is that since this was arbitrary, my choice of B here, I can have countable infinity of different choices for B, because there's countable many ways in which I can create symbol sequences built out of ones and K. I can order them into an infinite sequence. So there's countably many different ways of tinkering with the periodic orbit, which means that I will have countably many different homoclinic orbits to that single periodic orbit. Just think about that mass, right? So in fact, this is the final thought, that there exists, in fact, countably many homoclinic orbits. To the periodic orbit. So this is pretty amazing. And the reason was that B was an arbitrary string. Okay, so I stop for now, and this is where I'm going to continue next week. Any questions, please ask them now.
So I have one question where you were trying to encode the iterates of P. So can you go back a bit?
Sure.
Go a few pages up. So basically when you wrote down phi of f tilde P and you were trying to find out.
Right.
So here what I couldn't understand is this second point, which is f of HS0 is VS0. How do we get that?
That's a good point. That's in fact probably the hardest part of this to understand. The only reason is why I find that personally hard to understand, because we are so much focused on the symbol space now. We have transferred the whole problem to the symbol space, but we're discussing it, and this was the very first thing that we discussed about the whole construct, and by that time we tend to forget that, right? Because go back to the very first figure, right? So look at any of the HI, H2, right? What happens to H2? In the first step, it gets mapped into this one. Then you fold it over, so it gets mapped into that one. So under the map, H2 gets mapped to V2. And the same story holds for H1. H1 is mapped to V1. And that's all I'm saying in that line, right?
Ah, okay.
Right.
All
So
right.
F HI equals VI. I goes 1 to 2, right?
Okay, because I thought maybe we were making some arguments about, well, some arguments based on the map, but apparently not.
No, this is part of the definition of, this is in fact the only thing I pretty much know about the map, right?
Yeah.
But I agree with you, because I also, I don't know, when I don't look at my notes for years because I don't teach this course or whatever, then I say, wait a second, where is this coming from? And because it's simpler than what we would think, right?
Yes.
I think we can, it's just that it's really the very definition of the map, right? So for that reason, it's a very good question. I try to emphasize it, but I should probably even emphasize it more. Okay.
Right.
Anything else on this one?
No, I think apart from that, I understood the other things.
Okay, good.
I got another question.
Yes.
If you could jump back to the previous slide.
This one?
Yes, here. You state that P is an element of sigma. Shouldn't it be of lambda?
No, you're right. Thank you. Remember the rule: when I say something, I mean the opposite. So there's two spaces here involved. So yeah. So this is then the encoding of P. Thank you. That's it. That's confusing. Yeah. Anything else?
Well, one question. So,
yes.
I mean, based on what you showed right now, this construct in which you can get arbitrarily close to a periodic orbit. And well, the argument is that if you're in a periodic orbit there, well, you can have an itinerary into which you go into the past, you actually go away from the orbit. And that's how you argue about the instability, right?
Let's look at the argument again. So we're in agreement, hopefully, on this line, right?
Yeah.
So what I was trying to show here is that this S star, where I'm starting my construct, is distinctly different from any point on the periodic orbit, right? Yes. It's definitely off the periodic orbit because look, it's not a periodic sequence. It never will be, because B is different, right? Yes. So the way to picture it, it's somewhere here. As such, it has a finite distance from the periodic orbit.
Yeah.
Right? Whatever that is between the closest point, and so there's definitely a finite distance. Now, if I then start iterating S star, then it so happens that on this orbit, I'm able to get arbitrarily close to the periodic orbit in forward time and in backward time. Okay, So this looks like a good thing because I'm getting close to the periodic orbit in forward time. But what looks like a good thing for stability in forward time, if it also happens in backward time, it's a bad thing for stability, because it means that let's just drive this point arbitrarily close to the periodic orbit, arbitrarily close, right? So that means that you will be able to pick points that are as close to the periodic orbit as you want, and yet after a while they end up in a finite distance from the periodic orbit. That goes against the definition of Lyapunov stability that we had, because the idea of Lyapunov stability, which is very general and applies to orbits of maps as well, is that I should be able to keep initial conditions arbitrarily close trajectories arbitrarily close to my object, as long as I'm willing to keep the initial condition even smaller, right? We have basically drawn tubes, right? Remember? So I have to have the ability to stay as close as I want. Here I don't. No matter what I do, no matter how closely I restrict the neighborhood of the periodic orbit, there will be initial conditions that will reach this finite distance, right?
Yeah.
Therefore, it's unstable.
But there would also exist a sequence of symbols where you always get these A blocks.
That I always get these what?
The blocks A. So the way you constructed the periodic orbit, you took these blocks A and you just inserted some other block B.
Right.
But I could also imagine a sequence in which you always get an A, no matter how many times you shift the sequence to the left or the right.
I'm sorry, I didn't get that. I perturbed this sequence, right? So that B is in there, right? Forever. So that it gets shifted to the infinity, but it will never be identical to the periodic orbit.
Yes.
Right? That the A's start dominating for sure. But that little B somewhere in the tail, either in that direction, will always distinguish me from the periodic orbit. That just means that I can get arbitrarily close to the periodic orbit, but never hit it. Okay.
Yes.
So when you say you will always get an A, that's what I couldn't immediately get to.
No, I'm just imagining the sequence in which there is no B, just A's.
Well, if it's all A's, then you're just jumping around the periodic orbit.
Yeah.
Right. Doesn't contradict anything, right? We knew that there was a periodic orbit. If I restrict myself to the periodic orbit, then I'm on the periodic orbit. That's not a perturbation to the periodic orbit, right?
Yes.
Any choice of B which is different from A is a perturbation. Right?
Okay, so the point of this, this proof was just constructing a slight perturbation and showing that it could arbitrarily approach the periodic orbit.
Correct, in both time directions, yes. And if I only did this in forward time, then this would not prove instability. But since it's also in backward time, that proves instability, right? Approaching something arbitrarily close in backward time means instability in forward time.
Okay, thank you.
Okay, all right, welcome. What else? While you're thinking, again, the next office hour will be on Monday, the first one. You can already ask questions, and I'll take a look if I have covered enough to issue the first homework. I just want to see that. Generally speaking, those of you who took, no, this is not like nonlinear dynamics one, because here there's a deadline for the homework. Generally, there will be a 2-week deadline for the homeworks, and I need to see how I progress, and I need to see if I'm at the point now that I have enough material that you can do the homework. And then the purpose of the office hours is ask and answer questions about the material, the ongoing material, but also questions about the homework problems, and you will be getting answers, hints more like, right, not answers as to how you have to solve them, right? And then the idea is that with those hints and clarifications, you would solve them and turn in the solution. Once again, it will not be graded, but we will be using your copy that you turned in the oral exam, so that you will explain what exactly you've done, right? And that, of course, may lead to questions, me asking for clarification, things like that, just to check whether you had the right idea or right understanding of the definitions and procedures. So first office hours on Monday, and as I said, I'm working on getting access to the videos, but maybe I already have an email in the meantime to that effect. I'll let you know. Anybody else? If not, then thanks for today. See you next week, if not before.